Okay, we're going to talk about stationary points in this video. So stationary points are something that you'll need to know about to do the assignment. And basically, if you've got a function y equals f of x, then the stationary points are the points where f dash, which equals dy by dx, equals 0. In other words, stationary points are the points on a graph. So we have a graph like this, where the derivative is 0 or where the slope of the function is 0. And you should see that is very handy because it's actually going to be those points there. Pardon me. And those points there are the positions of minimum and local minima and maxima. So stationary points are very good for finding out in optimization problems, which is what we're doing in our assignment. So f dash of x equals 0, that's our stationary point. Now, if f double dash of x, which is your second derivative, so if you differentiate, again, the derivative, if that's greater than 0, then that implies that you're actually dealing with a minimum. If f double dash of x is less than 0, you're dealing with a maximum. Okay, so this is basically the definition of stationary points. So let's just sort of do a couple of examples. Here's just a fairly garden variety quadratic. So dy by dx is just going to equal 4x take 9. Okay, that's using our differentiation rule that we've got. We could use first principles on that, but it'd be pretty tedious, so we'll just use our law. And we put this equal to 0, and this implies that then 4x take 9 plus 9 equals 0 plus 9. 4x equals 9. Divide both sides by 4. We get x equals 9 on 4. So at this point here, we have a stationary point. The slope of this function here, up here, is 0, x equals 9 over 4. Now, if we have a look, we'll look at the second derivative. So there's our first derivative. Now, we know that dy by dx equals 4x take 9. Let's differentiate that, and we call that d2y by dx squared. And that's just going to equal 4. And 4 is greater than 0, so this implies we've got a minimum. Okay, x equals 4 on 9 gives a minimum value of y. Okay, for that value of x. And if we put x equals 9 over 4 back in here, we'd work out what that actual minimum value was. So that's how we use stationary points. The stationary point of this function is found by finding its first derivative and putting that to naught, solving for x, and then looking at the second derivative and seeing what the sign of that second derivative is. Okay, now I'm going to do an example which is a bit more of a practical example and a bit more like our assignment. So what I want us to imagine is a box. It's a pretty typical sort of problem we do with these sorts of things. A box where the surface area so the amount of material that you're making this box, you keep constant. So the surface area, our total surface area, is a constant. Now, we're going to make it so the height of the box is x, the width of the box is 2x, and the depth of the box is y. So we can come up with expressions for total surface area and volume. We've done this many times before. It's a very simple thing. We've been doing this sort of thing since year 8. I'm not a very good box, I'll draw on there. Okay, so total surface area. In this case, we've got this end and that end here is this end I'm pointing to here, and the end looking in that way. We've got two lots of those, and they're both x times y, so we've got 2xy. This side in here, looking in this face, and the one at the back is just x times 2x, so that's 2x squared, and we've got one in the front, one at the back, so that's 4x squared. And then looking at the side from looking at those two sides, we've actually got 2x times y, so that's 2xy, and we've got two of them, so that comes to 4xy, and we can simplify that to 6xy plus 4x squared. Okay, just make sure you understand how we got that. That's really very simple. So that's our surface area, and let's say we've got to make that equal to 20. Okay, and we're fixed with that. Okay, we've got a fixed amount of material that we want to make this box out of, but we want the volume of the box to be a maximum. So we want V to be a maximum. Pardon me. So we just come up with a very quick equation for what the volume of this box is, and that's easy for just a rectangular box. It's just length times breadth times width. So that's just going to be 2x times x, so that's 2x squared times y. So there's our volume. Now you probably think, what are we going to do now? So we basically, in the next slide, what I'm going to do is use this equation here. We'll call it equation 1. Call this equation 2. And I'm going to rearrange equation 1 to get y the subject of the formula, and then substitute back into equation 2. Okay, so I'll just erase all of that and start again. This is a similar sort of problem we've done before. We'll just go, okay, TSA equaled 20 equaled, what did we have? 4x squared plus 6xy. Okay, that was our surface area equation, and our volume was just 2x squared y. So that was equation 1, that was equation 2. So using equation 1, going to do a little bit of rearranging here. So we'll get with 6xy, going to take 4x squared from both sides. That's equals 20 minus 4x squared. So, and divide both sides by 6x, so we're going to get y equals 20 minus 4x squared all over 6x, sorry. Okay, so substituting this back into y, we're going to, substitute this into 2. We're going to end up with v equals 2x squared times 20 take 4x squared all over 6x. Okay, so there's our expression. Now we've got an expression for the volume of that, and it only relates to x. There's no y's in this anymore. So this is now going to come out, this equation. We'll just erase all that, start again. Okay, we've got the v now equals, it was, what did we have there, sorry, it was 2x squared times 20 take 4x squared all over 6x, and when we got a few things to cancel there, so that x is going to cancel with one of those x's there, and that's going to cancel and make a 3 there. So this is going to end up 20x over 3 minus 4x cubed over 3. Okay, so there's an expression now for our volume. So I'm now going to make that equal to, first of all, I'm going to find dV by dx. Okay, so that just comes to 20 over 3, because we're going to differentiate this with respect to x. minus 4 thirds and times 3x squared. That cancels. So this ends up with 20 over 3, take 4 lots of x squared. And to find the stationary points, that's going to put that equal to 0. So come back over here. Okay, we're going to go up here. This means that 4x squared, because I'm now going to solve for x. So x squared equals 20 over 12. Yep. So x equals the square root. And so that actually, let's make that 10 over 6. It's actually 5 thirds. So it's the square root of 5 over 3. Okay, and we're now just going to have a look to see. So there's our point. We're hoping that's going to be a maximum. So we're going to have a look at, very quickly, d2v by dx squared. And that's just equal to minus 8x. And if we put x equals root 5 over 3 there, we see that is less than 0. So this implies we've got a maximum. Okay, so that's basically how we do it. At x equals root 5 over 3, and we can substitute that back and find out all the dimensions of it, because we can find out using the equation for the surface area, we can find out what y is and what 2x was. We can find out the actual maximum value of the volume, but this point here, that's where, this is where the maximum occurs. So once again, we worked out, just tracing that back, we worked out this equation for volume. We differentiated it to give this, made it equal to 0 because that's where our stationary points are, and stationary points define our minimum our local minimum or maximum. We solved for x, got x here, looked at the second derivative and found that that was less than 0, so that meant that we were actually at a maximum, which is what we wanted. Okay, if you have troubles with that, just go back and go through the whole thing again.